If the engine is the heart of the ship, then the valves. They are the heart valves. If they don't open and close exactly when they're supposed to, at the exact pressure they're designed for, the whole system just goes into cardiac arrest.
And that's really the mission for this deep dive. We're going to ignore the big flashy pistons today and look at the circulatory system. We want to understand this hidden architecture of the engine room.
And it's not just plumbing.
No.
Yeah.
It turns where the guide starts with the most sort of fundamental choice an engineer has to make.
Okay.
Do you want to stop the flow completely, or do you want to control how much is flowing?
Let's take the jacket water, for example. The engine block needs to stay at a really steady beneficial water temp. It tells the computer, hey, we are half a degree too hot.
And the computer responds.
The computer sends a signal to the control valve. The valve uses air pressure to nudge the stem down just a fraction of an inch, letting a little more cold water into the mix. It's making thousands of tiny adjustments a day.
Wow.
It maintains that sweet spot of viscosity and temperature that keeps the engine efficient. It creates a level of stability that manual operation just can't match.
That's impressive, but it also feels a little trusting. We can get to that later. I want to shift gears to the protection section of the guide, because sometimes the fluid tries to fight back.
The one-way streets?
The check valve, or non-return valve.
Simple concept, vital function. It allows flow in one direction only.
Yeah.
If the flow tries to reverse, the valve slams shut on its own.
Why is reverse flow such a big deal?
Physics again. Imagine a pump that's pushing heavy sludge up a long pipe. If that pump stops, gravity takes over. That heavy column of sludge falls back down the pipe.
And hits the pump.
And it's the pump, spinning the impeller backwards. It can destroy the seals. It can burn out the motor when it tries to start again. The check valve is basically a trapdoor that protects the machinery from the weight of the fluid it just moved.
There is one specific check valve in this guide that really caught my eye. It sounds like something from a disaster movie. The storm valve.
I love the storm valve. It's such a great reminder that you aren't just in a factory. You're in a factory that is actively fighting the ocean.
Totally. So you have these pipes that discharge wastewater out the side of the ship, usually above the water line. But what happens in a hurricane?
The waves get higher. The ship starts rolling heavily.
Suddenly, that discharge pipe is underwater.
And not just underwater. A huge wave might slam into the side of the hull with tons and tons of force. Without a storm valve, the ocean would be forced up that pipe and right into the engine room.
You'd be flooding your own ship through its drains.
Which is why SOLAS, the Safety of Life at Sea Convention, mandates these. They have a weighted flap. The ship's waist can push it open and flow out. But if the ocean pushes back, the pressure slams that flap shut instantly.
It's a castle gate that only opens outwards.
It's a brilliant, completely passive defense system. It uses the ocean's own force to seal the ship.
Speaking of defense, we have to talk about emergency protocols, fire and explosion. And honestly, the guide cleared up a misconception I've had for years. I always thought safety valve and relief valve are the same thing.
Most people do. But in marine engineering, the difference is life or death. It all comes down to compressibility.
Gas versus liquid.
Exactly. A safety valve is for gases, steam, or air. Gases are compressible. If you heat water in a boiler and it turns to steam, it expands massively. You're basically sitting on a bomb.
So if the pressure hits the red line, what does the safety valve do?
It pops. It's designed to open fully, instantly. It's violent. A huge whoosh. It dumps a massive volume of steam to drop the pressure immediately. It has to be that fast, because the pressure rise in a gas system can be exponential.
Whereas a relief valve
Is for liquids, oil or water. And you can't really compress a liquid. So if the pressure rises in an oil line, you don't need a sudden explosion of oil. You just need to let a little bit out. A relief valve opens proportionally. Pressure goes up a bit, it opens a bit. It relieves the stress gradually.
So safety equals pop, relief equals ooze.
Essentially, yes. One prevents an explosion, the other prevents a burst pipe.
Okay, then we have the panic button, the quick closing valve, or QCV.
This is maybe the most psychologically intense valve on the entire ship.
Why is that?
Because its job
To save the ship.
to save the ship, right?
Yay!
But think about the engineer. Their entire job is to keep that engine running. The QCV is designed to stop it instantly. It's installed on the fuel tanks. If there is a major fire in the engine room, you have to cut the fuel source.
You have to starve the fire.
Exactly. But you can't run into a burning engine room to turn a wheel. That's a suicide mission. So the QCV is spring-loaded. It wants to be closed. It's held open by a wire or a hydraulic line that runs all the way out to a fire control station somewhere safe on the deck.
So you're standing outside.
You smash the glass, you pull the handle, and snap. The tension releases. Deep down in the engine room, the springs slam the fuel valve shut. The silence that follows is probably the loudest sound an engineer ever hears.
It's the "we are abandoning the engine room" switch.
It is. And you have to test them regularly. And every time you do, you just pray the wire doesn't snap by accident during normal operations. Because a blackout at sea is not fun.
There's one more dead man switch mentioned, the self-closing valve. This one seems to be designed purely because humans are. Well, we're flaky.
We get distracted, we get bored, we make mistakes.
And the job here is draining water out of the fuel tanks?
Yeah, you have to drain the sludge and water that settles at the bottom. It's a slow, smelly, boring job. If that was a normal gate valve, an engineer might open it, check their phone, walk away to grab a coffee.
And 10 minutes later, you've drained 1,000 gallons of diesel fuel into the bilge.
You get a massive oil spill, a huge fire hazard, and a very angry captain. A self-closing valve is spring-loaded. You have to physically hold the handle down to keep it open. The moment you let go,
It snaps shut.
it snaps shut. It forces you to pay attention. If you faint from the fumes, it shuts. If you walk away, it shuts. It designs the human error out of the equation.
Which brings us to the actuation part of the guide. We've talked about hand wheels and springs, but we also saw pneumatics and hydraulics. So, stepping back from the parts list, we had a mission to decode this circulatory system. And I think I see it now. It's not just about moving fluid around. It's about 4 pillars.
Control, regulation, isolation,
And protection.
and intentionality. That's what really stuck with me reading this. Every single valve is a conscious choice. Someone had to look at that pipe and say, we need a butterfly here because of space, or we need a storm valve here because of the waves. And we need a QCV here because if everything goes wrong, we need a way to save the crew. It's engineering that respects the danger of the environment. It acknowledges that the sea is always trying to get in and the fire is always waiting for a chance.
Here's the thought I want to leave you with, though.
Yeah.
We talked about that self-closing valve, the one that shuts if the human walks away. And we talked about the control valve, the brain, that regulates temperature better than any human ever could.
Right. Automation is the trend.
But the guide also hammered home that gate valves break if you use them for throttling. That relies on a crew member knowing not to do that. It relies on the human understanding the physics of wire drawing.
It relies on training, on experience.
So if ships are becoming more and more automated, are we approaching a future where no human hand ever touches a valve, where that judgment call is just gone?
We might be. But sensors fail. Wires corrode. Computers crash.
And when the computer screen goes black in the middle of the Pacific, you might find yourself really wishing you had a big, heavy iron wheel to grab onto.
And the knowledge of which way to turn it.
Thanks for taking the plunge with us today.
Safe voyage.